Well, good afternoon. Thanks for that introduction, and I'm very, very grateful to Eric in particular for extending the invitation to come and speak. I have transcended a number of disciplines over the course of my career, and made a relatively recent foray into physical oceanography. So, why am I standing up talking about oceans when I have absolutely no background in the subject? I've never taken a research cruise. I've never even driven a numerical model of my own. But I think there's a wonderful opportunity here to exchange ideas from the planetary science community and the limnology and oceanography community. And I know I've had a lot of fun learning new things and trying to grapple with genuinely new problems. And I hope maybe some of the tools and experiences you have may be able to brought to bear. So this is more of an advertisement than anything else. Hopefully it'll be a useful summary of what is really a very, very fast-moving field within planetary science. It's a business in which we literally do have to rewrite the textbooks every decade or so. But I would like to think that nobody should write an oceanography textbook anymore and confine it to the Earth, because there are bodies of exposed liquid under a sky that can generate winds, under a sky that has astronomical bodies that can force tides, that are in a different setting from that with which we are familiar. The same physics applies with an exotic working fluid, and different conditions, but it's the same process. So the takeaway is there are 3 seas on Titan, and there are hundreds of lakes, and if you're interested in studying lakes and seas, maybe they merit at least becoming passing familiarity with. It turns out, coincidentally, Titan being a moon of Saturn and not as big as the Earth, the Titan's seas are about the same size as the Great Lakes, and somebody, I think at NASA Center JPL, just made this juxtaposition showing the relative dimensions. I know a lot of what I talk about will be more or less unfamiliar to some or all of you. In the interest of getting through a lot of material, if there's a clarification question, if I haven't put the units on some plot, shout out. And we'll get that straightened out. But curiosity-driven questions, maybe we can hold to the end. There is a little bit of confusion in the words ocean or extraterrestrial ocean have been applied to layers of liquid water in the deep interiors of icy worlds. Titan among them, but most principally Europa. Which has attracted a lot of mission development attention because of the astrobiological potential of liquid water. I posit that Titan is a fundamentally more interesting place because it has an atmosphere, it changes with time, and there's more to observe, and that is reflected in the literature. Apart from the isolated moment when the Galileo probe arrived at the Jovian system and brought a lot of new data and research funding to the Europa community here, throughout the age of planetary exploration, and in particular while Cassini has been revealing new findings, Titan is quantitatively about 3 or 4 times more interesting than Europa. So let me just put that dig in there. For any of you who are amateur astronomers, you may have seen Titan with your own eyes through a telescope. It is about the smallest thing that you can see that isn't just a dot. With a good seeing and or a big telescope, you can see it's actually a little disk. And there's actually a Catalan astronomer in 1907 that saw that the edge of the disk was a little bit dark, which he took to be the inference that Titan had an atmosphere. It wasn't a hard edge like the edge of the moon. And you can almost see that in this webcam image taken with a 10-inch telescope. And there's Titan. It's a little dot next to its parent planet. But you can actually make useful measurements with even small telescopes, which is one reason there are so many papers published about Titan. If you take the light from Titan and spread it through a prism or a diffraction grating, so that's down here. This is a picture I took with a 8-inch telescope. So here's Saturn, here's Titan, and here is the first order diffraction, the spectrum of the light being smeared out with wavelength. Now when the astronomer Gerard Kuiper in 1944 did that with photographic plates and a prism, he saw these dark bits, these bands, and these match up with the absorption generated by the gas methane in the laboratory. So this told Kuiper and the world that yes, indeed, Titan did have an atmosphere, and that makes it unique among the moons of the solar system. Turns out most of the atmosphere is actually nitrogen. Methane is only a small component, rather similar to water vapor in our atmosphere, but it really is the only place that is like this. That motivated the development of the Voyager space missions in the late 70s. The 2 Voyager spacecraft flew by Titan in 1980 and 81, and in fact Voyager 1 was targeted to make a very close encounter of Titan because it has a methane atmosphere, and we knew that there were organic compounds in that atmosphere. There was a kind of, we knew the atmosphere had this orange smog in it, which is generated by photolysis of methane. And we wanted to measure how thick the atmosphere was by passing Voyager's radio signal through it. So Voyager 1 was actually sent close to Titan, which precluded going on to Uranus and Neptune afterwards. Had Voyager 1 failed, we would have actually retargeted Voyager 2 to do that measurement, and we'd have never seen Uranus and Neptune up close. I mean, it really was a scientific priority to understand how thick this atmosphere was. And indeed, we found that actually the sea level pressure is about 1.5 times that on Earth. We find this whole zoo, this is an infrared spectrum, and I forget what the units are, the wave number or something, in the mid-IR. I think this is about 12 microns wavelength. But you see there's this whole zoo of organic compounds, hydrogen cyanide, acetylene, ethane, ethylene, deuterated methane, HC3N, which I think is cyanoacetylene, propene. You know, there's just 20 here. With Cassini, we've actually discovered literally hundreds. And these are formed by the destruction of methane by ultraviolet light. And the puzzle that emerged is that the amount of methane in Titan's atmosphere should be destroyed in about 10 million years, only a fraction of the age of the solar system. So why do we see methane in the atmosphere today? Is it being buffered somehow? Is it being resupplied? And the idea emerged that maybe there's a surface reservoir, an ocean, a global ocean of liquid methane that is somehow replenishing the atmosphere. One of the main products, ethane here, is also a liquid at Titan surface temperatures, and so might accumulate, and maybe you'd have a global ocean that is getting progressively enriched in ethane. So the picture of Titan in a comparative planetology sense, I mean, it's a moon, it's not a planet, but actually it's more of a planet than many planets in some ways. It's bigger than the planet Mercury. There's Mars, Venus, Earth. It has a tilt, you know, an obliquity similar to Mars and the Earth, so it has seasons. It takes 29.5 Earth years to go around the sun, so the seasons are long. The gravity at the surface of Titan is about the same as the Earth's moon, so if you're an astronaut on Titan, you would bound around in kind of slow motion like the Apollo astronauts did. Most of the atmosphere is nitrogen. The sea level temperature, being so far from the sun, is 94 Kelvin. That 1.5 bar pressure and the 94 Kelvin mean the air density at sea level is about 4 times the air we're breathing here. So low gravity, thick atmosphere, it's a very easy environment to fly in, actually. If you were standing on the surface of Titan and strapped some wings to your arms, you'd be able to flap and take off. The practical implications of that have yet to be fully appreciated. The atmospheric structure is interesting in it's sort of directly analogous to the Earth's, but with very different chemicals and different numbers on the plot. So you have a surface temperature that's low because we're so far from the sun. Temperature declines with altitude and you get to the tropopause, and then you have a warm stratosphere above it. Now the greenhouse warming that leads to this warm troposphere is due to methane. So methane is not only a potential liquid on the surface, but it forms clouds, and it's a greenhouse gas. So it's a condensable greenhouse gas, which opens the possibility of interesting climate feedbacks that, if you warm the surface, then some of the liquid methane evaporates, you get more methane in the atmosphere, more greenhouse warming, that increases the surface temperature, and maybe you can have climate runaways and things. The reason the Earth's stratosphere is warm, sorry, I guess it's here, is the absorption of shortwave sunlight by ozone, which is a photochemical product of oxygen dissociation on Earth. On Titan, it's this organic smog that's produced by methane photolysis. So you have an anti-greenhouse effect due to the haze, which blocks some of the light, and you have a greenhouse effect under here. So there's a whole sort of seesaw of climate effects to explore here. There may be different levels of clouds with different compositions, but most of the haze that is kind of uniform makes this orange blob. Just going back one, it's what obscured the surface from Voyager's cameras. This is sort of more or less uniform. There's no discrete clouds. We've since observed with Hubble and ground-based telescopes discrete bright clouds in some locations that are, we're pretty sure, methane clouds, in fact, convecting methane clouds. But there's a whole zoo of cloud possibilities that are open because of the different molecules that are available. So this was all very exciting, but we hadn't seen the surface. We didn't know what was down there. Is there a global ocean that's replenishing the atmosphere? How does that chemical cycle work? So these were factors that motivated the development of Cassini, which is a joint European Space Agency NASA project, which is how I got involved as a European engineer. This is, I think, remains the most massive planetary spacecraft launched in the West. It was about 5.5 tons at launch. It's about the size of a bus. 4-meter high-gain antenna to send the data back to Earth. We're very far from the sun, no solar panels. We have to use radioisotope power sources. Some of the instruments are bolted onto the side of the spacecraft, which is a whole interesting story. And there's this probe, detachable probe, that was supplied by the European Space Agency to descend under the clouds, under the haze on Titan, and see what's down there. I like to show this plot, which kind of sort of explains a little bit why space exploration is expensive. Basically because there's lots of bits that have to be brought together. The way the European Space Agency works is it actually has to farm out contracts to the different member states in the same proportion that it gets budget from them. So, if you're a program manager, if you just want to build something and make sure it's going to work first time, just have the Germans do the whole thing. It'll be great. But what you have to do is have 30% of it built in France and 20% in Britain, and find 5% of stuff for the Belgians to do, and the Finns, and it's like one of those bad jokes where hell is where the police are German and the cooks are English and all that. But somehow you have to bring this all together with all these interfaces where where are the bolts going to go, what pins connect to what, the software interfaces, all that has to be figured out in advance, and it's all that coordination, all that engineering that is actually what soaks up dollars. So somebody figured out that this structure, this heat shield made in France, French ballistic missile technology, would mate with this Spanish structure here. This happens in a building in Germany. Somebody had to figure out that you hold it on this dolly. This dolly has to be able to fit through this door. All that those details have to be worked out years in advance. It's just an amazing coordination. But it all happened. We got to the launch pad, and we launched in 1997. I started working on it back here in 1990. This is Titan's year. So the orbit around the sun is slightly eccentric. It's about 10% closer near southern midsummer, which turns out to be quite important. It took 7 years for Cassini to get there. It flew by Venus twice, the Earth once, Jupiter once, got to Saturn in summer of 2004, almost, just over 10 years ago. Huygens was released in January. Cassini was designed to operate for 4 years, but it's been operated very carefully. We've husbanded the fuel as long as we can. We extended the mission for 2 years, and things were still going well, so we thought we would try to go for broke and go for the summer solstice, basically see almost 2 full seasons on Titan. So we're about here now, moving towards northern early summer. And Titan changes over that interval. We started to see clouds, as I mentioned, that are methane condensing clouds. and these were predominantly around the South Pole during southern midsummer at the start of the last decade. They actually disappeared shortly after Cassini arrived because the Titan's shy, and we were moving away from southern summer then. But this was evidence that the hydrological cycle is active today. There are other changes actually related to polar circulation that I don't have time to go into. Some of these changes now manifesting in the other hemisphere around Titan's south pole, which is now moving into winter darkness. There's this weird bilobed polar vortex cloud that has attracted some attention. Cassini arrived, as I say, in 2004, and one of the first surprises was just how complicated the atmospheric chemistry could get. Were you to fly a mass spectrometer through the Earth's upper atmosphere, you would find a half dozen molecules, CO2, N2, NO, a couple of others. But there's this zoo of organic stuff. This is a mass spectrum going out to mass 100, but there's actually lots of stuff way out there. The methane and nitrogen get broken up by UV and magnetospheric electrons and recombine in all kinds of ways. It's a chemical factory making all this stuff. This stuff lacks oxygen. Titan's atmosphere is too cold for molecular oxygen or water vapor or CO2 to be abundant. So as a prebiotic chemical factory, the atmosphere is sort of a dead end, but it's possible to imagine transient exposures of liquid water on the surface from volcanoes or whatever, where if you do this in the laboratory, if you take this Titan goop and add water, it makes very interesting prebiotic chemicals. Now, we don't know how far that can go, or whether any of this kind of chemistry can occur in a non-polar solvent like liquid methane. But it's clear that exploring Titan it has some astrobiological interest. Anyway, the Huygens probe descended in January of 2005, coming up on the 10th anniversary. I can't go past without mentioning my little bit of the probe. As I mentioned, I'm an aerospace engineer by training, and I did a little bit of my PhD developing this instrument called a penetrometer. It's literally finger-sized, pokes out to the bottom of the probe. We had no idea whether the probe would survive impact because we didn't know whether we were going to splash down into a liquid or smack into a solid slab of ice or what. But if we survived, then maybe we could interpret something about the surface material. There was actually a little sonar, down-looking depth sounder, in case we did land in a liquid. But when the data came back from Titan, this is the 512 bytes of data I waited 7 years for. It looked nothing like anything I measured in the laboratory before. I mean, this is gravel, kind of spiky, with the size and spacing of the spikes depends on the particle size. This is sand. When you push into, this is force versus time, this is 1/20th of a second. When you push your finger into sand, the grains lock together, so it gets harder and harder as you push in. Wet clay has this kind of flat signal. And what we got from Titan was, well, it was kind of flat, maybe a bit spiky, and has this spike at the beginning. So the best guess was something like packed snow, maybe wet sand, but there's this spike, and well, what could that be? Did we hit a rock? Was there a spark? Was there a crust? And we came up, you'd think after spending more than a decade working on a project, you'd be given a few weeks to consider the data carefully and develop some measured conclusions. But there were 80 of us scientists at the European Space Operations Center in Darmstadt that January evening, and there were 200 journalists outside. And so we got the data at 6 p.m. and they wanted a press conference at 11 p.m. So we had to come up with something, and we were sort of looking at this thing. So something soft with something hard on top. It's kind of like creme brulee. I then had to spend 10 minutes Googling to get the accents right, because French colleagues would never forgive us if we got that wrong. But the media loved that. The media loved food analogies. The headline in Nature magazine that week was "Titan team gets just desserts with creme brulee surface." But anyway, it turned out all for the best. We had no right to expect this picture taken by the probe, which is here. After landing, this is basically taken from the knee high. The spacecraft could have failed at impact. The parachute could have draped itself over the camera. Anything could have gone wrong. But actually, the probe kept working, and it sent back actually about 200 of this same picture, in which one of them has a little droplet. There's a little methane dew droplet that we think formed on the camera baffle. But this shows these kind of rounded cobbles, and the way you get rounded cobbles is by tumbling them in a vigorous stream. So this was an instant indication that Titan has been hydraulically modified. You know, there's rivers that flow energetically, at least sometimes. The ground actually turned out to be slightly damp. This is a mass spectrum which included some ethane and methane sweated out of the ground. We don't know when it last rained there, but clearly it rained sometime in the past. We found evidence of river channels. This is a radar image about 200 kilometers across. So you've got this very wide braided river channel system that basically is the sort that you form when the flow changes dramatically, as it would in a flash flood from a storm. And there's a whole different story I can get into about the hydrological cycle. This is a mosaic of images taken by the probe as it descended by parachute. This is a highland about 200 meters high, maybe about 7 kilometers across. You can see the river channels here and here. The probe landed about there. And off in the distance, you see these two stripes that didn't attract a lot of attention immediately. But when we observed Titan a few months later, Cassini is in orbit around Saturn, goes by Titan once every month or so. When we took a radar image in October of 2005, we found these very extensive parallel ridges that we figured out were dunes. Basically, they're 20 to hundreds of kilometers long, a couple of kilometers apart. You can look at the radar brightness and actually figure out that they're about 150 meters high. So these are the same size and the same shape as the biggest dunes you find on Earth, specifically those in the Namib or Arabian deserts. And if you're interested in sand dunes, I had a book come out earlier this year about dunes on Mars, Venus, Earth, and Titan. But you're here to hear about lakes, right? So I should really get onto that topic. So it was actually almost 2 years after Cassini's arrival that we finally found evidence of standing liquid on the surface. Cassini had been formulated with this sort of expectation of maybe a global ocean, but it turned out that Titan wasn't nearly so simple. It was only when we looked at the North Pole, which was at the time in darkness, again this is a radar image about 200 kilometers across, that we found all these lake-shaped dark spots. These are 50, 20 kilometers across, and the fact that they're so radar dark requires that the material in them be a very low dielectric constant material, like liquid hydrocarbons. What was interesting, though, is that you see a lot of lake-shaped depressions that don't have liquid in them. And one idea is that these depressions are maybe etched into the crust, like karst lakes that you find in Yugoslavia or Florida, for example. That's actually a bit of a puzzle because we don't understand the solubility of some of this stuff in liquid hydrocarbons, but at last there were lakes. Then not long afterwards, we found bigger lakes and seas. So that first picture was down here. Then when we saw this one, Ligiea Mare, and started to get insight into Kraken Mare, which is about 1,000 kilometers across, they really got the impression that there's actually a lot of stuff there, and these aren't just little patches of liquid. They're seas that have, sea-like processes like tides and waves and stuff, maybe stratification. We'll get into all that later. If you just take the naive view just by looking at terrestrial lake basins, that if a lake is 300 kilometers wide, it's probably about 300 meters deep, which is a guess. Then you find that the total volume of liquid in here is between 100 and 1,000 times of the hydrocarbon reserves known on Earth. It doesn't do us any good. There's no oxygen to burn the stuff in, but it's a nice takeaway number. What is surprising, though, is that the total amount of methane in this, if it is all methane, is still only a fraction of the amount of methane in the atmosphere today. These seas that we can map and measure do not solve the problem of what is keeping the methane in Titan's atmosphere over geologic time. So it may be actually that over geologic time, there's been squirts of methane from the interior. Sometimes there are wetter periods. Sometimes the methane, which is a greenhouse gas, has dried out. We don't know. We've got no way of constraining that history. But this is quite different from the Earth's oceans, where you have on average several kilometers of liquid, whereas there's only a few a couple of precipitable centimeters of moisture in the atmosphere. Titan, it's sort of the other way around. And that part of that story may explain why we see relatively few clouds on Titan. Basically, you get torrential downpours on Titan. That's what makes the river valleys, but you only get them once a century. So it's like Titan is to the hydrological cycle what Venus is to the greenhouse effect. It's a terrestrial terrestrial effect that's of great importance, and it's taken to a horrifying extreme on another world, which is, you know, one good reason for exploring the other planets. So what is this stuff like? Well, it's literally like natural gas. Liquefied natural gas is typically 95% methane, usually some ethane, the other stuff's been purified out. At 94 Kelvin, it has about half the density of water. Liquid methane is much less viscous than water by about a factor of 5. Liquid ethane is a bit more viscous. We don't know how much ethane, how much methane are in these seas. In thermodynamic equilibrium, it would be about ethane rich, maybe about 60-40, something like that. A lot of the other properties are really rather similar to those either of liquid nitrogen or to, you know, organic solvents like gasoline or toluene that you may be somewhat familiar with. So it's not incredibly strange stuff. You know, people build valves and pumps that can handle liquid hydrocarbons. You know, there's no magic here. It's just different. Now, one of the puzzles that emerged as Cassini went on really came to the fore in about 2009. Is that as the mapping coverage, we covered about 1% of Titan's surface with radar imaging each time we got to do that. So by about 2008, we'd covered 20% of the surface. As we saw all these little lakes and these big seas, or parts of them, in the north, and there's really not much going on in the south. There's one little patch there and this one here, which, because it's about the same area as on Lake Ontario, is named Ontario-Lacus. So, you know, as you may know, there's an international body that approves the names for astronomical features and geological features on planetary bodies. You know, the same outfit that brought you Pluto is not a planet anymore. They have a convention that, you know, bright areas on Titan are named after mystic lands, and they decided that the seas on Titan should be named after sea monsters. So we have Ligiea Mare, Kraken Mare, and this one is called Punga Mare, 3 seas. But that lakes on Titan would be named after lakes on Earth, which I foresee, at least in this community, becoming possibly confusing. But we'll, you know, deal with that as and when. This is, as I say, about the same size as Lake Ontario, but has very different physical character. But, you know, why are these two different? Why is one pole not like the other? There's no obvious reason in the landscape that should be the case. They're both at the same elevation, more or less, which is actually less than the elevation at the equator. There's no obvious subsurface reason, well, not that we would know anyway, but the thing that is different between the north and the south, and you know, if this thing's 100 meters deep, there's no way you can move all that fluid from one hemisphere to the other in one season. It's not a seasonal effect. Maybe some of the lakes, you know, fill to a meter or two over the course of the summer and then dry out. Maybe that happens, but you can't move hundreds of meters of stuff in one season. So it's not a purely seasonal effect. But remember, the northern summer is longer and cooler than the southern summer at present on Titan. And we know from the Hubble and ground-based images when Cassini arrived that the big clouds happen in summer. There's more rain in summer. So if the summer is longer and cooler in the north, then some of the models are saying that the liquid should accumulate in the north, which is what we see. But that astronomical configuration of the seasons, let me jump ahead, is not a permanent fixture. Just like the obliquity and the arrangement of the equinox with respect to perihelion on Earth varies over tens of thousands and hundreds of thousands of years, which are what drive the Kroll-Milankovitch cycles that push the ice ages in and out on Earth and give you the polar layered terrain on Mars. So on Titan, 30,000 years ago, it was southern summer that was longer and cooler. So maybe in the past, the southern hemisphere of Titan had more liquid. And in fact, it's coming back 2 slides to Ontario-Lacus. So here it is, about 250 kilometers across by 70 or so wide. We know from a radar measurement that the slopes are very, very shallow at the edge, just one part in 10 to the 3, one part in 2000. So you don't need very much of a lake level change to produce an observable migration of the shoreline. And in fact, there's the green line here is what was measured from an optical picture, actually a near-infrared picture that sees through the haze better, in 2004. And the blue line is the outline measured in a radar image in 2009. So you're not comparing apples with apples. These are measurements done in two different ways. But you can see the outline seems to have shrunk, and taking this slope into account, that's maybe a drop in lake level of a meter or so. It could be that this is just an observational effect, that because this is an optical picture, that there's more blurring in the atmosphere, and so the edge isn't it's exactly the same edge. But you can see that this difference isn't the same everywhere. It's bigger here than it is over here. So that maybe is suggestive of some sort of real change. So has the lake level on Titan dropped by a meter in 5 years? Maybe. Some people have disputed that. It is interesting that the slopes here are comparable with the very shallow slopes in playa lakes like Racetrack Playa in Death Valley. This is a picture I took from a light aircraft. There's even cliffs at the south end. You can see the morphology is actually very similar. You've got a sort of convex part here, which is an alluvial fan. It's more or less straight edge. There's cliffs at the south side with rocks skidding around here. Maybe there are rocks on Titan, we don't know. But this morphologically is at least consistent with a picture of something drying out, a sedimentary basin that is at best shallow and maybe is beginning to have its bottom exposed. So that's consistent with the long-term climate picture of the south drying out. Now, if we go to the north, look at Ligiea Mare, my favorite, you can see this very complex coastline. I mean, it is 300 kilometers across here. There's some interesting aspects of the configuration of these channels here that some people have drawn attention to that maybe suggest some sort of tectonic control. There's an oddly straight edge here. This stuff and this stuff is all flooded valleys, which obviously you get when the sea level rises. So, the south is drying out, north is filling up, maybe. And actually, if you look in detail at some of these morphologies, you can draw some very striking analogies with terrains on Earth that are sinking relative to the sea level. This is the north end of Oman, where the Arabian plate is diving under the Eurasian plate, and basically the land is sinking relative to the sea by 1 or 2 centimeters a year. And it's the spitting image at the same scale of what we see on Ligiea. So maybe Ligiea, the terrain around Ligiea is sinking, maybe the sea level is rising, but something's going on. Now, I like this picture. This was a TV film shoot I did at Lake Mead some years ago, where I'm gesticulating out of the open helicopter door, I might add, at the flooded valleys near Las Vegas. Now, the reason the lake level rose there is we built the Hoover Dam. But I'm also pointing out the bathtub ring. In the last decade or so, the amount of snow melt and precipitation has declined, so the water budget has let the lake level drop, and the lake has left behind the dissolved solutes, the salts, as this white bathtub ring. And we actually see something similar on Titan, around Ontario Lacus, in fact. There's this bright margin seen in the near-infrared. Many of the northern lakes also have bright margins that could be evaporite deposits, could be indicating that the lake level was higher in the past. So, we've got indications of higher lake levels and lower lake levels in the same area. So there may be a very complex history of a liquid budget going up and down. Maybe there's a combination of seasonal change, there's geologic forcing, the amount of methane in the whole climate system may have varied, and there's this astronomical pacing. So there's a lot going on, and we're going to struggle to disentangle it with what we have. There are maybe some indications of formerly larger basins in the south. Here's Ontario again. It looks like there's valleys that were cut up to a point and then they stopped being cut. So why is that? Is the slope change, or was that a former sea level? Don't know. Okay, how about tides? So the tides on Earth, very simply caricatured, are that the moon or the sun pulls a bulge, and because of the centripetal rotation, is bulges on both sides of the Earth, and the Earth rotates underneath that bulge. So the level goes up and down, twice every 24 hours. On Titan, things are a little bit different because, like the Earth's moon, Titan always has the same face pointed to Saturn. It's tidally locked, and it goes round Saturn once every 16 Earth days. So there would be a tidal bulge because Saturn's gravity is very big, and that tidal bulge would actually be 100 meters high. But Titan isn't moving relative to that bulge. The bulge would just sit there. But what does change is Titan's distance from Saturn. That orbit isn't circular. It's slightly elliptical, and so when you're closer to Saturn, the bulge is bigger than when you're further away. So the bulge, if there were a global ocean, will be growing and shrinking by about 10 meters. We don't have a global ocean. The sea basins are obviously rather restricted in their geographical extent. So the result is that Ontario maybe has just a few tens of centimeters of variation. Now, because the day on Titan is so long, this tidal forcing period is long in duration. You don't have resonant tides like you do on Earth. Basically the slosh in the basins like the Bay of Fundy is of the same period as the tidal forcing period, and so you get amplification and you get these 10-meter tides and tidal bores and all that fun stuff. Doesn't happen on Titan, unfortunately, just because everything's so slow. But there is a tide, as I mentioned, and now with some assumed bathymetry in the radar map that we now have that more or less is complete of Titan's large seas, you can start playing numerical modeling games. Take the Bergen Ocean model, as a colleague of mine in Germany has, and plug in Titan gravity, and plug in the density for liquid hydrocarbons, and plug in the tidal potential, and see what happens. And what you find is that there's maybe a 20 or 30 centimeter tidal cycle, which is respectable given that it's not amplified by any resonance. There's an interesting feature of the architecture of Kraken Mare, which is that there's really sort of two basins separated by this part, which may be where the most intense tidal currents exist. That strait is narrow enough potentially to restrict the transport of liquid through the gap. It turns out it's actually about the same size as the Strait of Gibraltar. There's a little sort of labyrinth of smaller channels in parallel with it, but the current in the straits here could amount to about 0.5 meter a second, which is pretty respectable for Titan. So maybe there could be currents that are enough to perturb the surface roughness. This is a picture I took from my homeland, Scotland, of the Corryvreckan. It's a strait off the west coast of Scotland between the coast and the Isle of Jura. George Orwell wrote 1984 from an island overlooking this strait. You can actually hear it roar from 10 kilometers away. So this is actually a beautiful, calm day. These aren't wind-driven waves. This is turbulence on the sea surface driven by the tidal currents. Maybe the throat of Kraken is like this at the right parts of the tidal cycle. We are just now, literally 2 weeks ago, I saw these results from Tetsuro Takano, looking now at wind-driven currents on Titan seas. The winds near Titan surface are probably of the order of 1 meter a second or so, and they can generate centimeter per second surface currents, a little bit less at depth. We are starting to wonder if these currents, which are maybe several millimeters a second at the seabed, these should be enough to lift sand-sized particles. So there may be resuspension of sediments from the seabed as at different parts of the seasonal cycle or different parts of the tidal cycle. And I was very excited to see some simulations of this sort of thing in Dmitry Beletsky's office earlier today. So I think there's some of these processes are happening on Titan, and by looking at what's going on in the Earth's seas lakes and seas of comparable size, we can at least instruct ourselves as to what isn't absurd, if not what is happening. Just one thing I published on fairly recently. I mentioned that if Titan seas were in thermodynamic equilibrium, they would have a composition that would be ethane dominated. The low or moderate humidity of the atmosphere must be in equilibrium with a suppressed methane vapor pressure. One way to do that is add involatile ethane, which basically acts like salt or sugar does. You know, when you spill syrup in the kitchen, it doesn't dry out, right? It just sits there being sticky and annoying for, you know, until you clear it up. Whereas water dries out. It's because the vapor pressure of water is being suppressed by the involatile solute. Ethane acts that way. Ethane can be thought of as salt or sugar, as an involatile solute. So if you look at the evaporation rates that some of the models would predict, and look at the precipitation that the global circulation models predict, you get a lot more precipitation at high latitudes by a factor of several. Maybe evaporation is similar throughout the domain, but you need to adjust something to stop the seas drying out as a whole. And even if you tune things so that the whole system is in equilibrium, that the evaporation rate matches the precipitation rate, you will have local disequilibrium, right? There's going to be more rainfall up here than there is down here. So, okay, it evaporates to balance that, but then that liquid has to work its way through this labyrinth of channels and down through the throat and evaporate here. So there's an export of fluid, and that fluid is more or less pure methane. It's been distilled. It's rainfall. It's like fresh water. And so you may flush all the solutes out of Ligiea and into Kraken. Now there's a little bit of tidal back and forth perhaps, so it's not a complete flushing, but the conclusion that you would get just by constructing an ethane budget and a methane budget is if you take the precipitation fluxes and modulate the evaporation fluxes by the areas and by the amount of ethane, the salinity if you like, then you find that taking as realistic numbers as we can come up with, Ligiea has to be several times less ethane rich than Kraken, which is a neat prediction that maybe has the prospect of being verified with Cassini measurements. There are ways of estimating the composition from dielectric constant and so on that may bear on this. Just moving on briefly to the observations again. This is a very iconic picture that was taken 2010, showing the sun glinting off. This is near infrared picture, showing the sun glinting off the surface of a lake that of course had to be named after a lake on Earth. So it was named Jingpo Lacus. Lake Jingpo is a lake in China that the translation is literally mirror lake. So, you know, we're being cute here by calling it a lake discovered by its reflection after a mirror lake. But the point is you'd only see this reflection if the sea surface were dead flat. There are no waves present. We have made the same measurement at Ligiea and at Ontario Lacus with radar in an altimeter mode that's very sensitive, and some voodoo processing that I won't go into tells us that the RMS surface height variation is less than 3 millimeters over large areas of the sea surface. So dead flat, which is weird because Titan has low gravity and it has a thick atmosphere. It should be easy to make waves. I even did the experiment once when no one was looking at a wind tunnel at NASA Ames of putting kerosene in a tray and blowing wind across it and seeing what wind speed you need to make the waves pick up. And, you know, sure enough, it's easier to make waves in kerosene than water because it has lower viscosity, lower density and all that. Nobody had done experiments like this before because so much terrestrial oceanography is empirical, right? You go out to the sea, you measure the wind speeds, you measure the wave heights, get a big cloud of points, put a line through it, you know what you need to know. Doesn't help you on Titan where the gravity is different and the fluid is different and all that. You need a better physical understanding. This wind tunnel experiment didn't go very far along the path to understanding that better, but it was at least a start. So what's going on? Either the liquid is somehow viscous, suppressing the formation of waves, and that's entirely possible at Ontario Lacus, which has been drying out, and it's left all the dregs, all the butane and the benzene and stuff behind, all this stuff. This is used sump oil. You can make a very good mirror out of used sump oil, it turns out. The other possibility is we're just looking at the wrong season. We're looking at the calm season, the winter. And the predictions are in the north at Kraken and Ligiea, that as we move towards northern midsummer, the wind speed should pick up above the threshold needed to generate waves, which is just about a half a meter per second. It's more in liquid ethane than methane because ethane's more viscous, so there's that uncertainty. And you can have calm days in the windy season and windy days in the calm season. It's going to be a stochastic thing, but maybe we should start seeing the waves any day now. And in fact, maybe we are. There was a paper published last year that looked at this patch of Ligiea Mare, which when we looked late last summer, had a bright spot in it that wasn't there before. Could be a whole number of things. Could be, a pumice raft. It could be some seabed exposure that was, just below the surface before, and the tides or wind setup has dropped the lake level so that we can see it now. Or maybe it's wind roughening of the surface, basically cat's paw. We don't know. We observed that area again recently, and something was still there, but it looked different. So I think we're leaning towards subsea sediment resuspension kind of questions. One other remarkable observation we did last year was we were looking for the waves again with the radar in its altimetric mode, looking straight down. And in fact, we got a bottom echo through something like 160 meters of liquid. Because it's a timing measurement, you can measure the propagation time and in further depth directly. And the fact that we were able to get an echo, a radar echo, looking through 160 meters of liquid, says that liquid is very, very transparent. And in fact, only liquid methane would probably do it. If there were ethane and bits of propane and other stuff, we probably wouldn't see the bottom. So that's at least superficial support of the idea that Ligiea is flushed by rainfall, that it's fresh, it's methane rich. I'm going to have to jump through this stuff very quickly. Some of you may have heard about a mission proposal that some of us worked on to send a capsule to float in Ligiea. And it was ultimately unsuccessful, as I'll explain, but really opened up a whole range of ideas and explorations for me that were loads of fun. Splashdown is a very easy way of landing on a planetary surface. Liquid surfaces are flat. There's no rocks, no gullies. You know what you're going to land in. That's why we used it for the Apollo program. Of course, you're splashing down into liquid hydrocarbons. We use computer models to evaluate the loads and research dynamics and so on. But you want to anchor those models in some real physical data. And so had some fun at a secret facility at Penn State doing splashdown tests. We wanted to measure the air-sea exchange processes. The wind speeds we'd measure with an ultrasonic anemometer. We'd have a camera to look at the sky, look at the waves, antenna to send the data back to Earth, temperature sensors. Below the waterline, we'd have a down-looking sonar, measure the turbidity, measure the dielectric constant, speed of sound, other things, and really try and get a sense of what's happening at that sea surface interface. It's really fun. I did not know what tone pilz meant. It's a German word for sound mushroom. When you design a sonar transducer, you need to couple the energy into the liquid, and you do that with this shaped cone, and you put a big heavy thing on the back end to reflect the sonar energy forward. And so the thing ends up looking like a mushroom, and the Germans invented it and called it sound mushroom. This thing actually used the same piezoelectric ceramic that I used in the penetrometer. It's actually from the same company in Southampton, UK, because the properties of this stuff are actually very good at cryogenic temperatures. We literally took our sonar transducer and put it in liquid nitrogen to show that it would work well at 80 Kelvin, and it actually worked great. These are some of the things you have to think about. There's a great simplification in designing instrumentation for Titan seas versus Earth seas, in that liquid hydrocarbons don't conduct electricity. You don't have to waterproof everything. That at least is easier. If you think you have a challenge, those of you who work in forecasting or climate prediction or anything like that, consider the question, how big are the waves going to be on Ligiea Mare on July the 2nd, 2023, when we arrive? Well, all you can do is say, the waves depend on the wind, so how big are the winds going to be on July the 2nd, 2023? Well, you don't know, of course. So you go to your friends who drive numerical models and you say, what do you think the wind's going to be then? And you go to your other friends who've got a different model that of course has slightly different predictions, and at least they all kind of converged in about the same realm. We don't expect winds to be much more than half a meter per second. Well, nobody cares what you think the wind's going to be. What can you be absolutely certain the winds are not going to exceed? Because we're going to spend $400 million on this, and we don't want it to go wrong. But we want your number to be as low as possible because we don't want to make it hard. Because if it's hard, then it'll be expensive and we won't get funded to do it in the first place. So you have this weird kind of tension in figuring out what these numbers are, but we kind of came up with 1 meter a second as the most likely utter maximum. 99% is the canonical number. Okay, so then how big are the waves going to be? Well, you can match wind speed to significant wave height, but that's just a statistical property. 1 in every 1,000 waves is going to be twice as big as that. So you get a Rayleigh model and figure out how often is the capsule going to be tipped so hard that the antenna gets pointed away from the Earth, and you have to figure out these communication outages and all that stuff. Really fun, really interesting. I didn't know about Rayleigh distributions before I got into all this. And we have people at APL, because APL does a lot of work for the Navy. It's not just building APL built the New Horizons spacecraft that will arrive at Pluto next year. It built Messenger, which is in orbit around Mercury right now and will crash into Mercury, I think in about 8 months' time. But it does a lot of work for the Navy on unspeakable things that I don't know anything about. But we have people at APL who do sonars, and we have people at APL who can simulate the motion of vehicles floating on liquids. And so we drove those tools with wave spectra, adapted from terrestrial wave spectra but scaled to the Titan numbers, and figured out how fast is this antenna gimbal going to have to move to stay pointed at the Earth. Figuring out where we go is an interesting question. Obviously we aim at the middle. We don't want to crash onto the land. We want to splash down where it's deep and safe, so we aim for the middle. But then where would we go? And actually the first person to figure out how fast a wind-blown floating object would move was Edmund Halley. Actually in the same year that he drew the first vector map of the trade winds, and his first discussion of the transit of Venus between the Earth and the Sun, which coincidentally happened the very day NASA was reviewing our proposal, but that's neither here nor there. But anyway, this is a question that mostly confronts iceberg hazard kind of questions. Because people either design their drifters to respond totally to the wind or totally to the currents, not something in between. There's a science flotsmetrics on the dispersion of stuff that falls off the side of cargo ships that does get into some of that. But you can take your GCM output and say, okay, where would we go? And there's 1,000 virtual splashdowns here, and then 1 Titan day later, the cloud is spread. And then after 3 Titan days, most are still at sea. But after 6 Titan days, 90 Earth days, our nominal mission, about half of them would have beached, which probably wouldn't have been a fatal scenario, but would enable some really interesting science. We looked at the topography, such as we have from radar stereo, and there are mountain peaks that would be visible from more or less the middle of Ligiea, actually. So you could have this great outreach effort of every week sending an update out to all the schools in the country saying, here's what we see on the horizon, here's where we were last, where do you think we are, putting pins on maps. There'd be all kinds of fun exercises to do. As I say, unfortunately NASA, and you can tell this is a sort of NASA-related slide because it's full of abbreviations, but NASA instead decided to send a French seismometer to Mars rather than do something brave and exciting. And in fact, we rely on a radioisotope nuclear power generator to do this mission. Titan is too far from the sun, it's too cold. We need the waste heat as well as the power from a radioisotope source. And there's actually a Department of Energy bottleneck in producing the fuel for this stuff. So we in fact can't go at the next opportunity. And so because it's beneficial to send the data directly back to Earth without having to pay for a relay spacecraft, we will probably have to wait to explore Titan seas until about 2040 when it's next midsummer there. That said, there's all kinds of interesting possibilities to think about. going to NASA Glenn next week to look at ideas for a Titan submarine. And if you have propulsion, you can think about, well, where would you go if you splash down in Kraken? Go up here, see if you can sniff the fresh water, the methane coming out of Ligiea here, swim back down, go through the throat. Maybe you have to wait, for the tides to be right before you can swim through. All kinds of fun stuff to think about. In the meantime, Cassini is still operating. We have, we're about here right now. There's still about another 20 or so Titan flybys. There'll be a lot of exciting new information to come out from those. But let me stop there so you can ask some questions and leave you with the point that there are lakes and seas. They're full of liquid hydrocarbons, which are important in the Titan climate system. They've probably varied over a whole range of time scales, maybe continuing to vary on scales we can see. It was very striking on this time development that the idea of sailing on an extraterrestrial sea grabbed people in a way that landing even on an asteroid or whatever doesn't grab people the same way. There's a whole different community you kind of engage with. So it'll happen sometime, sooner or later. These are very exciting scientific targets. But as I say, there's a lot I think we can learn about these processes that affect liquid bodies by studying Titan, and we can learn about those by studying the Earth. So let me, that's the wrong quote. Never mind. Let me leave you with that quote anyway. Thanks for your attention.
I think in my career, I think at one time or another, someone thought I did this. So when you start in the upper left-hand panel, what society thinks I do, what I think I do, what my grandmother thinks I do.